How's everybody doing? I'm Professor McElhoney. I'm a visiting professor here for analytical chemistry. I'm really glad I didn't wear that shirt today. This is the photo they take of all the new professors in the library, so in case you forgot what I was looking like. So from this blurb that's also in front of you, what you need to know is my research, if you want to get started, focused on ion selective electrodes for different settings. And by settings, I can mean water, I can mean soil, I can mean biological. It's kind of, they can be tailored to whatever environment we want. So what are ion selective electrodes? So I can talk about this slide probably for an hour. The AChem kids will probably get a longer talk about this stuff shortly. So whether or not you're familiar with potentiometric sensors or ISCs, you've used them. pH sensors and ISC. You're looking at H+. So you all know about ISCs, whether or not you've actually grasped it as an ion selective electrode. So that's what all these images on the side are. So these are the ones that you're probably familiar with. I know that the AChem lab, you're going to be using these type of pH meters soon. So we monitor voltage or potential as a function of time. And we utilize an organic membrane doped with an electrically neutral ionophore, or receptor compound, to look at a specific analyte. So we relate this potential change to activities in your bulk solution. So by looking at the change in potential, we can determine how much or a concentration of our analyte is. So I had a step funnel because I know most of the talks have been kind of organic or bio-based. So we would have an aqueous bulk solution. So if you had potassium chloride in your bulk solution, you'd have a membrane separating these two phases, and you'd have your organic phase, which is where your membrane would be. You'd have your receptor, which is seen here as a circle, and you could have an uptake of potassium by your receptor, in this case, which is right here, mitomycin is your ionophore for that method. And you'd have a buildup of positive and negative charge, and this potential change across your membrane is what used to detect our activity in our solution. So their applicability, ISCs, there's billions of measurements made by ISCs. I mean, every pH measurement. I mean, we're going to do, I think each AChem student is going to do a few pH measurements, and we're going to do ISC measurements. So you're already going to be adding to this number. So I saw this quote in a paper recently. In recent years, there's been over 20,000 papers published related to ISCs, which is quite a lot. And there's several different agencies that have standard methods that use ISCs. So there's the, if I can remember, the American Society for something method, technology methods, EPA, the American Public Health Association, the USGS, NASA. That's why I have a Mars symbol on my table. I made IFCs for potential Mars applications. And there's different things that you can make IFCs for: acidity, alkalinity, conductivity, ORP, nitrogen, salinity, pH, and there's just, I have a list down here, but there's many others that you can make. And I have mainly been dealing with alkalinity, acidity, and inorganic cations and anions. You can use also for biological applications. So why use them? There's low detection limits, so usually micromolar to sub-picomolar. You can have a large dynamic range, so you can go from maybe 10 to the minus 7 to 10 to the minus 1. They're selective somewhat, depending on what ionophore you select. They're quite stable if you practice making them. And they can be biocompatible depending on what materials you're using. And this is just right here, it's this figure. It's an example of some potassium electrodes. So we have our potential and our log, our constant activity of our potassium. So what my research, or what the research that would be done here, would be to take these typical ICs that are usually about the size of a pen and can be greater than 10 millimeters in diameter, and basically shrink them down. So if you came to my talk back in May, I had this picture. If you came to my talk, which no one did for no one here, I wouldn't expect anyone to come to my defense talk. You saw this picture. So this is a nickel, and on this nickel we have 3 different electrode housings. So these are typical to the ones that were flown on Mars. So they're about 6.5 millimeters in diameter. The next iteration that we used was around 4, and this iteration is just under 4. So the idea is to take an entire electrode. So you guys have all seen the pH electrodes that have been in Gen Chem, and I don't know if you've seen them or go. but in AChem, basically take that whole piece and make it this size. So what would a week in the lab look like, a week in the life of a student that would work with me? We would machine a lot of our own housing, so we can use either tie-down tubing, or we can actually fabricate different plastic pieces. You can compose a membrane cocktail using different organic species, fabricate the ISC, and then characterize it, so we can determine the stability. So it's a matter of just testing it over and over and over again and seeing if it's the same response. The sensitivity, is it still responding in the same manner that it always is? And is it selective? So if I have a potassium electrode, am I actually detecting potassium, or am I detecting everything else? And then again, Professor Leota said research. If there was no read, it would just be search, and it would be done. So we must repeat and improve. So if the sensors are behaving well, you can keep on repeating these tests and extend these characteristics, or you could go back and improve this with different methods. And my last slide, sampling. So I said we can use these for different things. So these are just a couple things. I Googled Ames Pond. I have no idea if this is the actual Ames Pond. You guys can tell me that. I think it looks a little big to be the Ames Pond over here, but that's just me. Deserts, you can go out and test different species that would be in soil for deserts. You can go out and put these sensors possibly in the ocean. There's several groups right now that are trying to make these sensors so that you can put them down a few hundred meters to look at different species in the ocean. You can go to Antarctica, look at different dry valleys or different snow melts, and also Mars. So this is a picture from Phoenix where soil was delivered and then analyzed by ion electrodes. So that's all I have.